Okay, some additional problems for chapter 11. Suppose we have a car and we know the car has some springs to it. If all of a sudden the driver hops into the car and the car goes down a certain amount, then we can figure out what the spring constant is going to be. And the car is going to go over a bump and it's going to oscillate up and down. And we're asked what is the frequency of the oscillations going to be. Well, we know that the frequency is going to be related to 1 over 2 pi the square root of k divided by the mass of the car plus the driver. And we can use the first part of the problem to figure out what the spring constant is. We know that when the driver got into the car, they compressed it, so we can write Hooke's law. The force due to the weight of the driver is going to be related to the spring constant as well as how far the length changed. So the force is simply going to be mass times gravity, and we have kx on the other side. Divide both sides by x, and we can isolate the spring constant k. One thing to be careful of is x is going to be 5 times 10 to the minus 3 meters. It gives that to us in millimeters. So k is going to be the mass of the driver, 66 kilograms, multiplied by the acceleration due to gravity, 9.8 meters per second squared, and then 5 times 10 to the minus 3 meters. That's going to give us a spring constant of 1.294 newtons per meter. Now I simply say, okay, the frequency of the oscillation is going to be 1 divided by 2 pi. Now I know what my spring constant is, and this should be times 10 to the 5th newton meters. It's going to be a very tough spring. So 1.294 times 10 to the 5th divided by the mass now of the car and the driver, 1766 kilograms, and the frequency of oscillation is going to be 1.362 hertz. For problem number 14, we're given an expression for the position as a function of time for simple harmonic motion, and we know that the general form of this expression is going to be position is going to be equal to amplitude times cosine of the angular frequency omega multiplied by time. And what we can do is we can pretty much directly compare these guys and answer part A by saying that the amplitude must be equal to 0.65 meters. For part B, we don't immediately know what the frequency is, but we know that the angular frequency is going to be 8.4 inverse seconds, and I know that the angular frequency is related to the linear frequency. It's going to be 2 pi multiplied by the frequency, so the linear frequency is going to be angular frequency divided by 2 pi, or 8.4 divided by 2 pi. The frequency then is going to be equal to 1.337 hertz. For part C, we're looking for the total energy, which I could either say that's going to be 1/2 k a squared, that's going to be at the maximum amplitude, or 1/2 mass velocity squared, that'll be at the equilibrium point. I also know that I can relate the angular frequency to the spring constant and the mass, and I know the mass and I know the spring constant, so I can say that this spring constant is going to be equal to omega squared multiplied by mass. So I can go with the first expression here and say that the total energy is going to be equal to 1/2 multiplied by omega squared multiplied by mass multiplied by the amplitude. So then my total energy is going to be 1/2 and 8.4, and make sure I square that guy. The mass is 1.15 kilograms, and the amplitude is going to be 0.65. I need to make sure I square this guy, and I'm going to come out with 17.142 joules. That's going to be my total energy. For part D, I'm asked for the potential energy and the kinetic energy when the position is equal to 0.36 meters. Well, I can pretty much use this expression right here. However, I would not be writing A, I'd be saying the potential energy is going to be equal to 1/2 angular frequency squared multiplied by mass, now multiplied by position. Make sure I square that there too. So 1/2 angular, or so 1/2 8.4, 1.15, and then 0.36. Now I got my squared, and I calculate out my potential energy to be 5.258 joules. Now, I know that the sum of the potential plus the kinetic is going to be equal to the total energy. So the total energy is going to be potential plus energy kinetic. So therefore, my energy kinetic is going to be equal to my energy total minus my energy potential. So 17.14 joules, subtract off 5.285 joules, and I'm going to come out with 11.88 joules is my kinetic energy. For problem number 36, it's fairly straightforward. I know that the frequency is going to be 282 hertz, and I know that the speed of sound is 343 meters per second. I know that the wavelength is related to the speed of the wave divided by the frequency. So 343 meters per second divided by 282 hertz, and I get the wavelength to be 1.22 meters. Now, number 53 is a little bit tricky because it gives us two frequencies. It tells us that they're successive, but it doesn't tell us they're necessarily which frequencies they are, and we're asked to find the fundamental. We know that we can write that any frequency is going to be a multiple of the fundamental frequency, but we don't know necessarily what that n is. However, if you think about it, if we think about two successive frequencies, we're going to have frequency of n and frequency of n plus 1. This is going to be n plus 1 frequency. Now what we can do is we can say I'm going to take a difference of these two guys. I'm going to say what is the change in frequency. So that's going to be frequency n plus 1 minus the frequency of n. So that's going to be n plus 1 multiplied by frequency minus n multiplied by the fundamental frequency here. Make sure I get all those fundamentals in there. And that's going to be n multiplied by the fundamental plus the fundamental frequency minus n multiplied by the fundamental. And this guy is going to cancel out that guy. So the frequency difference is going to be what the fundamental frequency is. So the fundamental frequency, therefore, is going to be 350 hertz minus 280 hertz. The fundamental frequency, therefore, is going to be 70 hertz. Problem number 57, rub-a-dub-dub, fun in the tub. So here I have a tub and I'm sloshing water back and forth, and it tells us I'm going to have a node in the center with antinodes on either side. And if you think about it, this is just going to be 1/2 of a complete wavelength. So the wavelength is going to therefore be 2 times the length of the tub, where that's going to be the length of the tub, which I know. It asks for the speed, and we know the relationship between the wavelength and the frequency. This is going to be 2 times the length of the tub multiplied by the frequency. 2 times 0.75 meters, I've converted it over to meters, multiplied by the frequency, 0.85 hertz. The speed, therefore, of this wave in the tub is going to be 1.275 meters per second.